Welcome to this week's first lecture in EE501. Remember, we have seen the concept of AX equals to B, how to solve it. And I'm going to start with a brief review of what we have done, and then we're going to see some special cases, as I promised you last time. So we start with an equation AX equals to B. Then we're asking the existence and the uniqueness of the solutions. We are asking such questions. And if B is in the range space, then there exists a solution. If B is not in the range space of A, then we know that we don't have an exact solution, but we can find an approximate solution by calculating B1, which is the projection of B onto range space of A. Okay? Then we solve the equation AX hat equals to B1. We definitely know that such an equation has at least one exact solution, but we can still, so this was called the minimum error or the least square solution, and we can have infinitely many solutions, and in that case, what we would like to do is to find the minimum norm solution. And it is found by the following fact. So we have x1 hat, which is the minimum norm solution. It can be found by projection onto null space of A, orthogonal complement of an arbitrary solution x hat to this equation. With the fundamental theorem of linear algebra, we have seen that null space of A orthogonal complement is nothing but range space of A Hermitian. So I can write the same thing as follows: A Hermitian x hat. This is the same vector that we are finding. So this is just a review of, so this is called the minimum error, minimum norm solution, or minimum least square minimum norm solution. Okay? And I will first remind you some facts about the matrix A, and then we will see some special cases. A is a linear transformation from Cn. This is the domain into Cm. This is the range or the codomain, and null space of A is a subspace of the domain, and range space of A is a subspace of the codomain. Okay? We are going to use this picture in the coming topic. So let us now look at some special cases. So the special case one is A is full column rank. What does this mean? This means that all columns of A are linearly independent. How many columns of A do we have? So the number of columns of A is n, which is the number of columns, and m is the number of rows. Okay? So we see that when A is full column rank, then we have n linearly independent columns of A. So let us write all columns of A are linearly independent. Okay? In this case, A has to be a tall matrix or a square matrix. So I can write actually A, I can show A in this manner. Then X is going to be a small vector here like this, and B is going to be a large vector like that. Okay? So this is our A, and I have m rows and I have n columns. All right? And in this case, we know that m has to be larger than or equal to n. So either we have equality or there are more rows of A than there are columns. Okay? Why is this so? So in this case, let me try to show you. Suppose that A is a fat matrix like this. Okay? Suppose that A has some elements here, A, B, C, D, E, F. A is a fat matrix now. Now I am asking you the following question. Can this matrix have all of its columns linearly independent? So I see that the columns have two elements, and as a result, the columns are in C2. Okay? In C2, there are at most two linearly independent column vectors. There cannot be more. Okay? That means that only two of these columns can be linearly independent, and the third one should definitely be linearly dependent with the earlier ones. Okay? So that means that a fat matrix cannot be full column rank. Okay? A fat matrix like this. So either the matrix should be a square matrix or it should have more rows than columns. Okay? So now let me look at the meaning of this fact. M is larger than or equal to n. This means that, so remember we have equations here. For each row of A represent an equation related to X. Okay? So how many unknowns do we have and how many equations do we have? We have as many equations as the rows of A. So M equations. And how many unknowns? The elements of X are unknown. That means that we have n unknowns. Okay? So that means that we have more equations than unknowns. Equations than unknowns. Okay? So actually, we might not have a solution for this system because there are more equations than unknowns. Such equation systems are called overdetermined. Overdetermined. There are more equations than necessary to determine the unknowns. Okay? In general, n unknowns can be determined with n equations, but here I have m equations which can be larger than or equal to n. Of course, more equations than unknowns or equal. Okay? Equal number of equations to unknowns. Okay? But more equations than unknown is the case of an overdetermined case. So I can remove m equals to n from the overdetermined case here. So this was just some background information about this. Now I can actually start with the theory. Suppose that I would like to solve such an equation with a full column rank A. Okay? In that case, how can I apply this theory? Okay? The first thing that I'm going to look at the dimension of the range space of A. What is the dimension of range space of A for this case, for full column rank case? So the dimension of range space of A is going to be the number of linearly independent columns of A. And what is the number of linearly independent columns? Because all columns are linearly independent, this is going to be n. All right? And here, what is going to be the dimension of the null space? I know by the rank nullity theorem the following. Dimension of range space of A plus dimension of null space of A is equal to the number of columns. Okay? That means that this is equal to n, and this means that dimension of null space of A should be, what should be the dimension of null space of A? It should be equal to 0. Okay? So from this information, from the full column rank information, we get the following fact. Dimension of null space of A is equal to 0. That means that null space of A is a zero-dimensional space, which means that in the null space of A, there is only the 0 vector. Okay? So I have the 0 vector. Of course, this is the 0 vector of Cn. All right? So as soon as I obtain the null space of A equals to the 0 vector, I will be able to say something about these facts. So remember, the uniqueness of the solutions of this equation is determined by the dimension of null space of A. If the dimension of null space of A is equal to 0, then we have a unique solution when we have a solution. And if the dimension of null space of A is strictly larger than 0, then we don't have a unique solution. We have infinitely many solutions. So we have found here the full column rank brings us the property of dimension of null space of A being equal to 0. That means that in this case, if we have a solution, then that solution should be unique. If we have a solution, then the solution is unique. Okay? It is the property of full rank A matrix. In this case, I can actually talk about the properties of A a little bit more. Since null space of A is equal to a subspace which is composed of only the 0 vector, then I would definitely know that A is a one-to-one transformation. A is 1 to 1. I know this fact as well. And in this case we have, and that is actually proving also the uniqueness of the solutions. When we have a solution, then the solution is going to be unique. Okay? But of course we might not have a solution at all. Okay? In that case, uniqueness is not really meaningful. So suppose that if B is in range space of A, then there exists a unique exact solution. Exact solution. Okay? The uniqueness comes from the full rank property. And if B is not in a range space of A, what am I going to do? I'm going to apply that projection, this first projection, to calculate B1. B1 in this case is equal to projection onto the range space of A, the vector B. B really does not have to be inside the range space of A in this case. And as a result, when it is not, then we are going to try to obtain the least square solution. So we will project B onto range space of A. And we know that in Cn I can do this using a projection matrix. Projection matrix onto range space of A times B. Now, how can I find the projection matrix onto range space of A? I can actually calculate it. PRA is equal to B Hermitian B inverse times B Hermitian. Okay? And B should be composed of the basis vectors of the subspace that I would like to project onto. So I need to choose B such that its columns are basis vectors, linearly independent, basis vectors for the subspace I would like to project onto. And in this case, I can actually find such a basis quite easily for range space of A. So how can I find a basis for the range space of A? I need to look at the column space of the matrix. I need to take the linearly independent columns. That would give me a basis. But I know that all of the columns are linearly independent, which means that I can just form my B matrix with the columns of A. But that means that B matrix should be equal to A. Okay? So in this case, in this specific case, when A is full column rank, B can be selected to be equal to A because all columns are linearly independent. All right? So that means that my projection matrix, P range space of A, is going to be A Hermitian A, inverse A Hermitian. All right? And now using this projection matrix, let us project B. B1 is this matrix times B. It is going to be same matrix and this one. So this is my B1 and this has to be inside the range space of A because this is a projection onto range space of A. Now I can actually try to solve the following equation. A times x hat, this equation, A times x hat is equal to B1. B1 is this thing, A Hermitian A inverse A Hermitian B. So I need to solve this equation for x hat. Okay? And in this case, I want an analytical formula for x hat. Here it's not really difficult to find such an x hat. So consider that I take this term on the right to the left. Okay? A x hat minus A Hermitian A inverse A Hermitian B is equal to 0. This is the 0 vector of Cm in the codomain. Okay? Then I can take A parentheses x hat minus A Hermitian A inverse A Hermitian B is equal to the 0. But this means that this vector that I'm multiplying A with is in the null space of A. Okay? What does that mean? I know that null space of A in this case is composed of only the 0 vector. Okay? Which means that this vector which is inside the null space of A should be the 0 vector. Okay? So that means that X hat minus A Hermitian A inverse A Hermitian B should be the zero vector of the domain. Okay? And that means that our X hat is given as A Hermitian A inverse A Hermitian B. So this is our least square solution, minimum error solution in the case when we have a full column rank matrix. Okay, so this matrix so we have an analytical formula now. If I multiply B with this matrix here, then I would get my minimum error solution. Okay, so that matrix has a specific name, A Hermitian A inverse. A Hermitian is called the left pseudo-inverse. Left pseudo-inverse of A. Okay? This matrix has this specific name. And when I multiply this matrix with B, then I find my minimum error, the least square solution. Now I can ask you the following question: is this solution unique? The answer is yes, because in this case the null space of A turned out to be equal to zero dimensional, and null space of A is composed of only the zero vector. So there is no non-uniqueness issue in this case. So this X set is the unique minimum error, minimum norm solution. But suppose that here I really don't know what suppose that I really don't know this theory, and suppose that I want to continue the process. Suppose that I want to do this projection, okay? What would the result of the projection be in this case? If I still try to continue x1 hat, projection onto null space of A orthogonal complement, X set, this X set, in that case, what would be the result of such a projection? Let me try to answer that question. So in this case, null space of A is zero dimensional. What is going to be the dimension of the null space of A orthogonal complement? I know that null space of A, the subspace, is living in Cn. If null space of A is zero dimensional, then the dimension of the null space of A orthogonal complement is going to be n. I know that Cn can be written as null space of A plus orthogonal direct sum, null space of A orthogonal complement. And the dimensions should match here. Dimension of this thing is n, and dimension of this thing is 0 here. And therefore the dimension of the null space of A orthogonal complement should be just n. Okay? Null space of A orthogonal complement is also living in Cn. All right? In Cn, which is n-dimensional, I have null space of A orthogonal complement, which is also n-dimensional. Then what can I say about null space of A orthogonal complement? The null space of A orthogonal complement in this case is nothing but Cn. The whole space. Why is that? Null space of A was this set, which is composed of 0. For null space of A orthogonal complement, I need to find all vectors in Cn which are orthogonal to the 0 vector. And we know that all vectors in Cn are actually orthogonal to the 0 vector. Okay? That means that null space of A orthogonal complement is going to be Cn in this case, full column rank case. Then what is going to be this projection? x1 hat is equal to projection onto Cn X set. If I want to project a vector onto a vector in Cn onto Cn, if the vector that I would like to project onto a subspace is already inside the subspace, then the projection should be the same. Remember, the projection was the closest vector inside this subspace to the vector that I would like to project to. The closest vector in the subspace that is to this vector is going to be the vector itself. It is in the subspace already. Okay? So that means that the second part of this procedure really does not bring anything. It doesn't make any harm of course, but it doesn't bring anything new either. So if you don't know the theory, after calculating the minimum error or least square solution, you can continue to obtain the minimum norm solution, but it is going to be the same as the minimum error solution in this case. So in this case, what would be the projection matrix? Making this projection, PCN. Projection matrix onto CN. What is the projection matrix? Projecting all vectors in CN into CN. This is going to be the identity matrix. Okay? So if you try to do this projection, then you need to calculate the projection matrix like this, and whatever basis you choose, the projection matrix is going to turn out to be the identity matrix. So when you multiply X set with the identity matrix, you would get X set. All right? So that completes this first special case. Okay? It was the special case of columns of A being linearly independent, full column rank A. Now let us look at the second special case. The second special case is the case when A is full row rank. That means all rows of A are linearly independent. In the earlier case, we had columns linearly independent, and in this case, we have rows of A linearly independent. In this case, you can see that the A can be only a fat matrix or a square matrix. Okay? A fat matrix is something like this, and we have a large A, the X, and we have a small B here. Okay? So here M is the number of rows and N is the number of columns. And in this case, we need to have M should be smaller than or equal to N. Okay? Why is that? We have already seen the reason for the full column rank case. In this case, it's not really different. So if I have a tall matrix, A, B, C, D, E, F, if I have a tall matrix like this, can the rows of this matrix, can all rows of this matrix or such a matrix be linearly independent? The answer is going to be no, because the rows are in R2 or C2, and therefore there can be at most two linearly independent rows here. And the third row should be linearly dependent, whatever I do. So not all rows of a tall matrix can be linearly independent. That means that our matrix should satisfy some property like this. The number of rows should be smaller than or equal to the number of columns. Okay? Let us look at the equations here. So M is the number of equations and N is the number of unknowns. And in this case, we need to have the number of equations is less than the number of unknowns. Okay? Or equal, of course. Or equal. All right? So there are less equations than necessary to determine, or equal equations, or there are less equations than necessary to determine these unknowns. That is why in this case, this special case is called the underdetermined system of equations. Underdetermined system of equations. Okay? So now let us try to obtain the property of this AX equals to B problem. All right. So we have written everything that we can write for it, and then now we can try to examine the dimensions of the null spaces, range spaces, etc. Okay. Now, what does the property of full row rank say to us? So it says that all rows of this matrix are linearly independent. What was the row space of a matrix? We know that range space of A is the column space of the matrix. And what is the row space of the matrix? It is the range space of A Hermitian. So dimension of range space of A Hermitian. What should be this dimension in this case? So this is the row space of the matrix, because the columns of A Hermitian are the rows of A, the conjugate of the rows of A. And I have here, this dimension should be equal to M, because all rows of A are linearly independent. So this thing is equal to M. If the matrix A has M linearly independent rows, then how many linearly independent columns is it going to have? If the number of linearly independent rows, which is the row rank, is M, what is the number of linearly independent columns? That is dimension of range space of A here. Okay, what is this dimension? Number of linearly independent columns. In the last lecture and last week, we have said that number of linearly independent columns and linearly independent rows of a matrix should be equal. All right? And that is the rank of the matrix. So that means that this dimension should also be equal to M. All right? So what does that mean? Range space of A is an M-dimensional subspace of Cm. Range space of A is a subspace of Cm. Then, and the dimension of range space of A is just M. I have a subspace of Cm with the same dimension as Cm. Then what should be the range space of A? It should be nothing but the Cm itself. So from this property, from the row rank property, we are concluding that range space of A is nothing but the whole codomain of the matrix. Okay? Range space of A covers this whole space. All right? Which space does B belong to? So this is my B. B has M elements. So B is an element of range space of A. B is an element of Cm. But range space of A is equal to Cm. That means that B should be an element of range space of A. Okay? So in this case, we have a very nice property. Since range space of A is the whole space, this B vector should always belong to the range space of A. Okay? And what does it tell us in terms of the solutions? It tells us the solution, an exact solution of such an equation should always exist. Okay? That means that there should always exist an exact solution. Okay? In the earlier case, when we had a solution, it needed to be unique, and in this case, we always have to have an exact solution. Okay? But of course, now we don't know about the uniqueness at all. All right? So let me try to apply the procedure here. So I will calculate B1. Suppose that I don't know this theory, and suppose that I don't know the earlier theory that I have written here, but suppose that I'm applying this procedure blindly. Then what am I going to do? I will calculate B1 by projecting onto range space of A B. Okay? And range space of A is Cm, and the projection of B onto onto Cm is nothing but B itself. So in this case, B1 is going to turn out to be the B vector itself, because the projection matrix PCM has to be the identity matrix, because we are trying to project onto the whole space. All right? So now, therefore, actually we really do not have to apply the first steps here, because range space of A is already the whole space, and I really do not have to. But if you like to spend time, why not? So here so this first step, I really do not have to apply it. The next step is going to be obtaining a unique solution. Obviously, depending on the null space dimension of this matrix, the solution might not be unique. Okay? So suppose that I find a single solution xset to this equation. Okay? Suppose that I find a single solution xset to this solution. I know that the solution should exist because B is in the range space of A. So I can find always a single xset. Then what am I going to do? I'm going to try to project this xset onto null space of A orthogonal complement. But I know that projection onto null space of A orthogonal complement is projection onto range space of A Hermitian. These are the same spaces. Projection onto range space of A Hermitian xset. Okay? Now I have to find the P projection matrix onto range space of A Hermitian. Okay? And I need to multiply it with xset. And then find the minimum norm solution. Okay? So here, in order for me to be able to find P range space of A Hermitian, I need to find the B matrix. And this B matrix, if I know it, then I can calculate my projection matrix using this formula. Okay? So, and this B matrix should be composed of the basis vectors of range space of A Hermitian. Range space of A Hermitian is I know that the row space of the matrix, okay? The linear span of the rows of the matrix. And I have to find the basis for the span of the rows of the matrix. So I need to find set of linearly independent vectors which would span the range space of A Hermitian, okay? So the row space, which vectors would span, which linearly independent vectors would span the range space of A Hermitian? I need to put those rows into the columns of B, okay? And then I need to do this multiplication. The Gramian is not invertible if B is linearly dependent, B has linearly dependent columns. So into B, I need to put the basis vectors, which should be linearly independent. All right? So what are the basis vectors for the rows of A? I know that all rows are linearly independent. As a result, a basis for the row space of A are nothing but the rows of A. Okay? They are already linearly independent. I know it because of the full row rank condition. As a result here, I can choose my B composed of rows of A in the columns of B. Okay? But that is nothing but B equals to A Hermitian. Okay? I put the columns of A Hermitian into my B, and the columns of A Hermitian are the rows of A. I'm already trying to find a basis for row space of A. Okay? So let us substitute this specific B here. P, range space of A Hermitian, is, instead of B, I will write A Hermitian. B Hermitian is A, and B is A Hermitian. Inverse and B Hermitian is A. My projection matrix, for this specific case, would be in this form in terms of A. Okay? Now I'm going to actually do this projection now. So xset 1 is equal to the projection onto range space of A, this matrix. I have A Hermitian, A Hermitian inverse and A here, times xset, an arbitrary solution to the equation. Okay? So in this case, we have again a fantastic equation which can be given a meaning here. So here, what is A times X set? X set was an arbitrary solution to the equation AX set equals to B. That means that AX set is nothing but B. So this is B. That means that my X1 hat is going to be A Hermitian, A Hermitian inverse times B. This is the minimum norm, minimum error solution, the unique solution. Okay? And you see that we have again an explicit formula for this case. Okay? If I know B, if I know A, just substitute this A and B there and then find your result. No subspaces, no orthogonal complements or anything like, no projection matrices, anything like that. So you just find your result. All right? This specific matrix multiplying B, A Hermitian inverse, is called the right pseudo-inverse of A. Okay? And in this case, we have this explicit formula. Okay? In the earlier case, in the first special case, null space of A was 0 dimensional. Therefore, in that case, I told you that A was 1-to-1. A was a 1-to-1 linear transformation. In this case, range space is Cm. So this range space covers the whole of the codomain. Okay? And what does it mean for the A, for the matrix A? In terms of linear transformation properties, if range space covers the whole codomain, what does it mean? It means that A is onto, in this case. A is onto. Okay? In the first case, A was 1-to-1, and in this case, we have A onto. Okay? But that finishes the second special case. Okay? I will now just look at the third special case. A is both full column rank and full row rank. Okay? So in this case, we have both of the properties in the special cases 1 and 2. Okay? So I have both full column rank and full row rank properties. So A has the columns of A. All columns of A are linearly independent, and all rows of A are linearly independent. Okay? So we have this property. So all of the properties that we have seen for the earlier cases should hold at the same time. What does that mean? Remember, we need to have M is larger than or equal to N for full column rank property, and we need to have M is smaller than or equal to N for the full row rank property. But when both of these inequalities are satisfied at the same time, what can I say? M should be equal to N for this case. So we have, in this case, we need to have a square matrix. So A is a square matrix. It is not a fat matrix, it's not a tall matrix, it is perfectly a square matrix. Okay? And the other properties that we have found should also hold. So the null space of A should be composed of only the zero vector, and range space of A, this is coming from the full column rank property, and the range space of A should be just Cm. And the other properties should hold as well. Okay? So this means that the A is 1-to-1 and A is onto. And what did we find for the first case, full column rank? Then the solution is always unique, and for this case, there always exists a solution. And these properties should hold at the same time. So in this case, there always exists a solution, and this solution is unique. Okay? So in this case, we have both of the good properties of the earlier special cases. So I'm going to say one last thing about A here. In this case, the A, linear transformation A, should be both one-to-one and onto. Okay? One-to-one means birebir in Turkish, and onto means örten in Turkish. If a linear transformation is both birebir and örten, what can you say about that linear transformation? If a linear transformation is both one-to-one and onto, what can you say about that linear transformation? We did not teach you this in this course, but you might have seen earlier. If a function is both one-to-one and onto, then that function should be invertible. Okay? There needs to be an inverse of that function. So therefore, in this case, the one-to-oneness plus the fact that the linear transformation onto brings us the invertibility. Now we can talk about the invertibility of the matrix A. Okay? And that tells us that we can find A inverse. We can find A inverse. In the earlier cases, we might have some rectangular matrices, and for rectangular matrices, the inverses are not defined. There are, of course, these pseudo inverses that we have calculated, but they are pseudo. Yalancı in Turkish. Okay? They are not actual inverses, but they are pseudo inverses. They satisfy only some properties of an inverse matrix, and they do not satisfy some other properties. All right? So in this case, A inverse exists, and that means that if I write the equation AX equals to B, I can find the solution. Both X hat and X hat 1 should be A inverse B. Okay? So in this case, we have this perfect result, and actually the earlier cases would be a generalization of this specific case. Okay? In one of the earlier cases, I had calculated, for example, X hat equals to A Hermitian A inverse A Hermitian times B. Okay? This was the first special case, and in this case, if A is invertible, what can I do? A Hermitian A inverse A Hermitian. If A is invertible, then I can write this single inverse of the multiplication as the multiplication of inverses. Okay? So I can take this inverse by changing the order. So A inverse times A Hermitian inverse times A Hermitian. Okay? These are cancelling, and because the multiplication is identity matrix, then we have A inverse. So the left pseudo-inverse matrix turns into the actual matrix inverse, okay, when A is invertible. When A is rectangular, this is a pseudo-inverse, not the actual inverse. But when A is square and invertible, then this left pseudo-inverse turns into the actual A inverse. And the same is true for the right pseudo-inverse as well. If the matrix is invertible, the right inverse should also turn into the right pseudo-inverse should also turn into the actual matrix inverse. Okay? So that is, so I can say here, left and right pseudo-inverses turn into A inverse for this case. So therefore this is a specific case of the earlier cases. I have more properties on top of the special cases, the corresponding special cases before. Okay? So in this case, our solution exists and unique, and it is the minimum error, minimum norm solution. So now let us see the last special case. It is not actually a very, very special case because it is quite general. But the special case 4 is A is neither full column rank nor full row rank. So in this case, unfortunately, we have no shortcut. Okay? In the earlier cases, we have found some special shortcuts into which we can substitute A and B, special formulas into which we can substitute A and B and find our solutions, or unique minimum error, minimum norm solution. But in this case, there are no special shortcuts. Okay? So in this case, we have to apply the whole procedure. This whole procedure. We have to apply the whole procedure. Okay? In this case, this. And I'm going to illustrate the procedure on a simple example. Let us write example. So we have the following A matrix: 1, 1, 0, 0, 1, 1, and 1, 2, 1. Okay? And I have x1, x2, x3, and I have 1, 0, 3 here. So this is my A, this is X, and this is B. Okay? Now let us try to concentrate on the properties of this matrix. The first thing that I'm going to do is to look at the null space and range space dimensions. Okay? What are these dimensions? So I will write here the dimension of range space of A is the number of linearly independent columns of the matrix, or number of linearly independent rows. It really doesn't matter. How many linearly independent columns does this matrix have? So we see that these first two columns cannot be written in terms of each other. As a result, these first two columns are linearly independent. What about the third column? I see that the third column is nothing but the summation of the first two columns. That means that the third column can be written as a linear combination of the first two columns, which means that the third column is linearly dependent with the other ones. All right? So here, that means that our A is not full column rank. But what is the dimension of the range space of this matrix? How many linearly independent columns do we have? And in this case, this number is 2. Either these first two columns or last two columns, or the first and the third one, would be a basis for the range space. So what about the null space in this case? Dimension of null space of A. So according to the rank nullity theorem, summation of the rank plus nullity should be the number of columns, 3. Okay? And therefore, the answer here should be 3. And what about the null space dimension then? It should be just 1. Okay? There exists only a single non-zero vector in the basis of the null space. All right? Therefore, the dimension of null space is 1. So now what can I say about the existence and the uniqueness? In this case, really, I can definitely say that the solution, if we can find one solution, then that solution will not be unique because of this property. Okay? Null space is not zero dimensional. That means that the solution, if we can find one, it's not going to be unique. Okay? And dimension of range space of A is 2. That means that if B can be or might not be inside the range space of A, it depends on the B vector. So let us look at this B vector. Can I write this B vector as a linear combination of the columns of A? So I can actually look at only the first two columns. Can I write this B as a linear combination of the first two columns? I know that the first two columns would be a basis for the range space of A, and if B is inside the range space of A, then I need to be able to write this B as a linear combination of these two columns, first two columns. Okay? So can I do that? 1, 0, 3 is equal to, the first column is 1, 1, 0, and the second column is 0, 1, 1. I know that if this number is 3 here, I need to put here 3. If this number is 1, I need to put here 1. But this result really makes 1, 4, and 1. Really, 1, 4, and 3. Okay? So they are not equal. As a result, such an equality really does not exist. All right? That means that this specific B is not inside the range space of A, which means that I need to project this B onto range space of A to be able to find an approximate least square solution. Okay? Let us try to project B onto range space of A. B1 is projection onto range space of A of B. Okay? And I can do this using the projection matrix P range space of A B, and I know that P range space of A is equal to B Hermitian B inverse B Hermitian. And now I have to find a B matrix which would be composed of the basis vectors of the subspace that I would like to project onto. And in this case, can I choose B equals to A? In this case, the columns of A are linearly dependent. That if I do that, then I will not be able to invert the Gramian matrix. Okay? So as a result, I cannot do this anymore. Okay? Because the columns of A are linearly dependent, and if I choose B equals to A, then I will not be able to invert the Gramian matrix B Hermitian B. Gramian matrix would be non-invertible or singular in that case. So then how can I choose my B? I need to use only linearly independent columns of A. Okay? Range space is the column space of A, and that means that I need to find a basis for the column space of A. The first two columns would constitute a basis. I can take these first two columns, but equivalently, the first and the third columns would also constitute a basis. Similarly, the second and the third columns would also constitute a basis. Okay? So therefore here there is not a unique selection here. There can be many different selections, and here just because the numbers are all 1 here, I will choose the first and the second columns, okay, which are linearly independent, 1 1 0 0 0 1 1. Okay? And in this case, these columns would form a basis for the range space of A, and they are linearly independent, obviously. Okay? So now let us calculate B Hermitian B. It is equal to 1 1 0 0 1 1, and B is 1 1 0 0 1 1. In this case, this is going to be equal to 2 and 1, 1 and 2. The Gramian matrix should be always symmetric. So if you calculate this element, then you also know the other element as well. All right? It is actually, if you are working with real vectors, it is symmetric. If you are working with complex vectors, it is Hermitian. So its Hermitian is itself. So in general, this element should be the complex conjugate of this element. All right? So now I have to take the inverse of this matrix. This is equal to, I will use the standard formula here. The determinant is 3, 1 over 3. I will change the places and the signs, 2, 2, minus 1, minus 1. Okay? So now I'm ready to calculate my projection matrix here. So P range space of A is equal to, I will put 1 over 3 here, and it is going to be, I have B 1 1 0 0 1 1, and I would have this matrix 2 2 minus 1 minus 1. It is B Hermitian inverse with this 1 over 3, and I would have B Hermitian 1 1 0 0 1 1. I will not do this multiplication in the long way. I will cheat from my notes here. I will put these notes into the class. You will be able to download them. So if you would like to see, really you can check those. So I have 1 over 3. The result is 2 1 minus 1 1 2 1 and minus 1 1 2. Okay? So this is our projection matrix. Now I can multiply B with that matrix. So B1 is P range space of A times B, and in this case it is just pure algebra here. So it is 1 over 3 times that matrix here, 2, 1, minus 1. 1, 2, 1, and I have minus 1, 1, 2 here. And this is going to turn out to be 1 over 3 times, I will just erase this. This is going to turn out to be equal to 1 over 3, and I would have minus 1, 4, and 5. Okay? So this is our projection. This vector is surely inside range space of A. Okay? So I would have, so therefore I can solve the equation AXZ equals to B1. Let us write this equation 1, 1, 0, 0, 1, 1, and 1, 2, 1 here. And I have x1, x2, x3 equals to 1 over 3 minus 1, 4, 5. Okay? Now I need to, so these are the elements of xz. This is, maybe I shouldn't write just x1 hat because we already have one x1 hat. So I will keep the result as x1, x2, x3 for them not to be confused with the x1 hats. But you need to know that this is our xz now. Okay? Now I have to find at least a single solution to this equation. I know that there exists a solution. If there doesn't exist any solution, then maybe you have made a mistake somewhere along the way. In this case, there should definitely exist a solution. Okay? Let us find a single solution. Here I will assume that x3 is equal to 0. So xz, I will put this as 0, and I will find x1 and x2, which would satisfy this equation. I see that x1 should be minus 1, and I see that here this x2 should be just 5. Okay, and I need to have a 1 over 3 in the front. Okay, so this is a single solution of this equation. Okay, minus 1, 5, and 0. Okay? So this is our least square solution, one least square solution, and we know that it is not unique because of the null space dimension here. In order to get rid of that non-uniqueness, we have to make another projection. But before that, this was a first way of solving the first steps of this question, finding the minimum error solution. Instead, I can apply a second method, which is usually easier. Second method. And I'm going to use one of the special cases for this, for applying this second method of finding the same vector here. Okay? So I know that my equation is like this, and I know that the third column is redundant here. Okay? So I can just assume that x3 is equal to 0 in my solution. Okay? Suppose that x3 is equal to 0. And suppose that I remove this linearly dependent column from here. You can remove other dependent columns, so you can remove the second one as well. But since in my earlier solution I have chosen these first two columns as my basis vectors, I'm going to remove the third column, and I will write the following problem. 1, 1, 0, 0, 1, 1, and I would have here x1, x2. I assume that x3 is equal to 0 from the start. Okay? And then I'm writing here 1, 0, 3. Okay? Now if I can actually find a single x1 and x2 minimizing the error of this problem, I would find exactly the same vector here. Okay? Of course, I would find a two-dimensional vector, and I need to add x3 equals to 0 to that vector. Okay? But this problem is actually better than the original problem. Solving such a problem is easier than solving such a problem. Why is that? Why is that problem easier than this one? Because that matrix there is full column rank. Okay? So now let us call this matrix as A1, and I have x1, x2 here, and I have 1, 0, 3. A1 is full column rank. Okay? And as a result, I can apply my theoretical formula for special case 1. Okay, what was that formula? Xset was equal to A Hermitian A inverse A Hermitian times B. And in this case, A means A1. Okay, so I have just this one. So now let us try to solve this. A1 times A1 Hermitian times, this is my earlier B vector. Okay, so this is B Hermitian B inverse. It is the same matrix. So this is 1 over 3, 2, 2, minus 1, minus 1. And A1 Hermitian is just this thing, 1, 1, 0, 0, 1, 1, times our B. B is 1, 0, 3. Okay, let us do this multiplication. 1 over 3, 2, 2, minus 1, minus 1. And this multiplication is going to be 1, and I would have the second element is equal to 3. 1, 3. Okay? And this is going to give me 1 over 3, 2 minus 3, minus 1, and I would have 6 minus 1. It is 5. It is the first two rows of this solution. Okay? As a result, I can find Xset equals to 1 over 3 minus 1, 5, 0. Because X3 was 0 here. I selected it to be 0 from the start. Okay? This is also another method, and you see that it is a little bit shorter. But of course, applying the original one is perfectly valid. So now I have found a single solution. Then I will go to the second part of our solution methodology. So here, this solution is definitely not unique because null space of A is one-dimensional. It should be zero-dimensional for a unique solution. Okay? That means that I need to project this onto range space of A Hermitian in order to be able to find the minimum norm solution. Okay? So now let us write A Hermitian. That is 101, 112, and 011. Okay? This is our A Hermitian, and I would like to make a projection onto the range space of this matrix. Okay? So I know that I can do this by multiplying the Xset with the projection on matrix on this space. So I need to find P range space of A Hermitian. Okay? So P range space of A Hermitian can be obtained as B Hermitian B inverse and B Hermitian. And now what I have to do is to find B here. Okay? B has to be composed of the linearly independent columns, which are the basis vectors for the subspace that I would like to project onto. I need to project onto the column space of this matrix, and we see that the column space is the span of these three columns, but I know that one of those vectors are linearly dependent with the other ones. So you see that the second column is the summation of the first and the third column, okay? So the second column is definitely linearly dependent with the first and the third one. So therefore I can choose these first two columns or the last two columns or the first and the third columns, okay, as my basis vectors. Okay? So here, in order to be able to make everything easy, I will choose only the columns which are composed of 1. Okay? 0, 1, 1. These two columns would form a basis for the range space of that matrix. Okay? So now all of the operations are similar to the earlier one. B Hermitian B, it is going to turn out to be the following. Actually, it is going to be a very similar matrix. Yes, it is the same. 2, 2, 1, 1. And inverse of this thing, B Hermitian B inverse, is 1 over 3, 2, 2, minus 1, minus 1. And finally, our projection matrix is going to be P, range space of A Hermitian, is, I would have B here, 1, 0, 1, 0, 1, 1. I would put that 1 over 3 in the front. And I would put this matrix, 2, 2, minus 1, minus 1, times B Hermitian, 1, 0, 1, 0, 1, 1. Okay? And you can do this multiplication yourself to obtain the following projection matrix. 1 over 3, 2, 2, 2. I have minus 1, minus 1, 1, 1. And I would have 1, 1. Okay? And then all I have to do is to multiply this matrix with this individual solution here. Okay? So x at 1 is going to be this matrix times this solution. 1 over 3 multiplications would make 1 over 9 times this matrix. So I have this one times that solution. Minus 1, 5, 0. And this is going to turn out to be 1 over 9, minus 7, 11, and 4. Okay? This is the unique minimum norm, minimum error solution of our problem. So you see that the procedure now is much longer and you don't have actually a directly applicable formula. So, but that really completes this lecture, in which we have seen all of the special cases, and in the next lecture we're going to be going into the new subject, and that subject is going to start our journey to a specific matrix form called Jordan canonical form. But that's all for this lecture. Thank you for watching.